Okay, so the work I'm going to talk about today will be situated also in cosmology context, what Andrea talked about before, but more towards renormalization. And the work I'm going to present here is kind of rather recent. It's based in collaborations with a bachelor student and a master student in Regensburg, but kind of conceptually is based on something that I've been working on back here in Warsaw from 2014 to 16. Okay. So in a nutshell, again, we're going to do coarse graining, and we want to do it in a certain way using a local group structure of SU11. How we're going to do that will become clear later. Okay. So let me first tell you why this is interesting. So we know that renormalization is necessary in quantum field theory, so it is most likely necessary also for quantum gravity. However, it is largely ignored currently in both new quantum gravity and new quantum cosmology, not mainly because people are not aware of it, but because it is very complicated. So we heard a little bit about it from Benjamin Barr and also from Thomas Kuhn this week. So since it is very complicated, analytically tractable models are very welcome, and today's talk will be about an example of an analytically tractable model where you can do all the computations and you can see what changes if you take renormalization into account. So what we do today is we do coarse graining or renormalization. Those will be used kind of interchangeably in these terms. For cosmological spacetimes, so we're not going to consider general scenarios, but homogeneous and anisotropic spacetimes, because there our methods can be used. Again, the technical basis will be the Lie algebra of SU11. Why that will again become clear later. And everything we will show later can be transferred to the new quantum cosmology Hilbert space, or rather many copies of the new quantum cosmology Hilbert space, because we want to coarse grain many systems into one system. So what is new here, as kind of opposed to previous years or other works, I think we have the first example of an analytic many small spin to few large spin renormalization. So for example, when Benjamin Barr was talking, he was saying that they were working in the large spin regime completely, so they were coarse graining large spins to even larger spins. Here you can start with the slowest, with the smallest possible spins, so states peak around spin 1/2 and coarse grain them all the way up to large spins. And it also turns out that this is the region where the interesting stuff happens. So if you're already at large spins, not much happens, but the transition from very small to kind of medium large spins is the interesting one. So then we will show in the end that we have an analytic form for renormalized Hamiltonian, which acts on large spin states but captures the dynamics of the many small spins. So this will be kind of computed analytically. And we will also compute at a certain for a certain observable, which will be the critical density at which the bounce happens, the error that you make if you neglect renormalization. Okay. So then let us start with conceptually introducing coarse graining in new quantum cosmology. How should it work? So if you're doing cosmology, often you would work with a non-compact spatial slice. This box here is supposed to be that slice. And then you introduce something like a fiducial cell, and so you use iterations to that. But the size of this fiducial cell is a priori kind of unknown, or you can choose it however you want, and you would like to have your computations independent of that. And then, for example, what you could do is you could split this cell into others, into many cells, for example, one cell into 4 cells, and that would be what you would call a refining move. At the same time, say you have 4 cells. You would like to consider the coarse dynamics of those 4 cells. So for example, the total volume of those cells, you would do some coarse graining to like one large cell. So in the kind of language of spin systems, that would be a block spin transformation, or you could also call it a renormalization step if you want to talk with the renormalization group. Okay. And what we're going to do here is we're going to coarse grain today n copies of loop quantum cosmology systems, so one system in each cell. For now, since we're talking about the loop quantum cosmology context here, we want to have a homogeneous universe, so we're going to assume that the quantum states in all of those sub-boxes here are the same. So due to homogeneity of the spatial slice, all the quantum states should be the same here. And then coarse graining is done by adding extensive quantities. Yeah? So the total volume of the box is the sum of the volumes in each of the individual boxes here. So also expectation values of the complete volume are the sum of the expectation values of the individual volumes. And then you can also ask, can I maybe use such a setup also for different things? And there's, for example, a paper by Edward Wilson Ewing, which was kind of not considering this coarse graining picture, but just fixing many loop quantum cosmology cells like that. Then you can add some interactions and do some cosmology with that. I just want to mention this here for completeness that such a setup where you put many copies of the LQC Hilbert space has been considered also in such a context. I also want to talk about this from the loop quantum gravity point of view, or for a full theory embedding point of view of such cosmological models. In particular, this was the work that I was doing here in Warsaw. So from a full quantum or loop quantum gravity point of view, what we would say is, say I have some region of my spatial slice, I have some spin network there, which is represented here with a single vertex of that spin network. There will be some volume concentrated at that vertex. And then I can again ask, can I refine such a state? I could refine this box into 4 boxes with 4 vertices. And then again, given the quantum state on those 4 vertices, I can ask, if I coarse grain that into a single vertex, what would be the effective dynamics for that single vertex? Yeah. And then everything that is written here is pretty much the same as was written on the previous cell. So the quantum state that would be on such a vertex here, that would be the same at every vertex. We do the homogeneity assumption. This is very similar to what people in group field theory would do, so they call this a group field theory condensate. You would again add homogeneous quantities, so the volume operator acting on each of the vertices would just be added, and that should be reproduced by the volume operator acting on that vertex here. You again have no interactions between cells. So when you set up your model, or when you set up your cosmology as an embedding into a full quantum gravity model, you could, for example, show by taking the quantum states at all vertices to be the same, that inhomogeneous operators, for example, spatial derivatives, they will vanish briefly in such states. So you could kind of solve that part of the Hamiltonian constraint if you would like it by doing this homogeneous ansatz. And then one kind of central result of these years was that you can build these full theory models with adapted variables that are very much the same as the variables used in loop quantum cosmology. You use the very same gauge fixings that you use in loop quantum cosmology. And then you can make this kind of full quantum gravity model in such a way that at a vertex you have a loop quantum cosmology Hilbert space. Yeah? And then that gives you pretty much the same picture as you had on this side. Just that, well, at every vertex, you now have the loop quantum cosmology Hilbert space. It's actually precisely the same thing. Yeah? So the upshot here is that you may think of this either as some full quantum gravity theory, where you do this coarse graining, where your states are homogeneous, or you think of it as just putting many copies of the loop quantum cosmology Hilbert space next to each other. Yeah? So for what follows, these 2 points of view are kind of interchangeable. Okay. So then, let me talk a bit about these SE11 techniques, because they will be key in what follows. And as we saw on the first slide, there are 2 papers associated with that. And those 2 papers will be first this section 2, this SE11 techniques, and then the next paper will be the implementation of the LQC Hilbert space. And it turns out that the problem of coarse graining can be solved very generally if you're demanding some kind of relation to the SE11 algebra of your physical system. And then in the second stage, you can apply that to quantum cosmology with finding certain precise operators that realize that. And this is also how we're going to do it in this talk. So we're going to derive the results quite generally for SE11. And then later, we're going to show how this can be made work in the context of LQC. Yeah, so what we're doing is something that you could call group quantization. That was applied in LQC first time in 2012, and the idea is the following. We have a group, we have SE11. This is just as a reminder. They have certain algebra relations. They are written here in terms of Poisson brackets, but you can also write commutators here if you want. SE11 is very similar to SU2. Differences, since it's non-compact, there are many more classes of representations. We're here interested in a certain discrete class, which is also labeled by a spin j, running from 1/2, 1, 3/2, and so forth, all the way to infinity. The difference here is that, of course, the unitary representations are interdimensional, so the magnetic quantum numbers, they're not restricted between -j and j, but they start at j and then run up all the way to infinity. Yeah, so this is the main difference between SU2 that we need to keep track of. So then the idea of group quantization is very simple. It's just saying, assume I have a physical system with some set of observables, and those observables form a Poisson algebra that is isomorphic to SU11. Yeah, so you're kind of in this case up here, where you have three physical quantities. Here they're just called Kx, Ky, and Jz. They could be, for example, the volume in the cosmological setting, the Hamiltonian, and what is known as the complexifier. We'll come to that later. And if they form the algebra of SU11, then quantizing the system is very simple because you just need to look up the representation theory of SU11. Yeah? So you just say your Poisson algebra is the algebra of a group, therefore the representations of your system are the representations of that group. Yeah? So therefore the representation problem is very simple because you just quantize in a representation of SU11. Yeah? And the representation label here will be this capital J here, so the label tells us which representation we're in, and then coming to this relation to what we're interested in, this quantum number M, which will be the quantum number of this Jz operator, the Z component of the angular momentum if you want, that would be the volume. Now you see the volume, it starts at this spin J and then goes all the way up to infinity. So this means if you go to higher J representations, then you're effectively putting a lower cutoff on your volume. Yeah? So the lowest allowed volume is always J, and then you can have all the higher volumes. So this kind of already suggests that maybe this J is something like an RG scale. Yeah? It's kind of the scale of the lowest resolved volume that you may have in your system. Okay. One thing I forgot to mention here, you would also like that the dynamics of your physical system is generated by a linear combination of these observables here. That will be kind of a very useful technical thing later, and that will be also the case in this cosmological system where one of them will be the Hamiltonian, or the gravitation part of it. So then you quantize your system, as said before. This is very simple because you just need to look up the representation theory. And we're choosing these representations of SU11, which are labeled by this spin here. We have this Jz operator. It acts on such states by just multiplying the magnetic quantum number. And you have again raising and lowering operators, which give you the state proportion to n plus minus 1. And of course, if you act with the lowering operator on the lowest possible state, that gives 0. Yeah? So this is again very similar to SU2, just n is growing starting at J. Okay. So now you can put some states on this Hilbert space, which you want to use to compute expectation values, and we will use a certain class of coherent states, the standard Peredorov coherent states, which are given by such an expression for SU11. So what you see here, we are in representation J, so we're summing over the basis elements in representation J, which are labeled by this M. It starts at J and goes all the way up to infinity. And then we have some coefficient here. This coefficient is labeled by two complex numbers, Z0 and Z1. Yeah, and then we just kind of evaluate this here, and this gives you your coherent state, and this is a perfectly fine kind of coherent state. It has kind of linear spread, etc. Okay. So now you can start computing expectation values, and remember the idea from the previous page was that this J should be something like an RG scale. And it turns out, you can look up these expectation values. This is for the computation that has been done many times before. If you take an operator which is a linear combination of your three generators, then this expectation value will be J times some function that depends only on these complex numbers here, on this what we call spinors. Yeah? So what you see here is there's kind of a split in J, which is a prefactor, which you could consider as kind of an extensive scale of your system, and some function of Z, which you can consider as an intensive scale of the system. Now, for example, if you increase J, then the expectation values of all these operators increase. And again, something I forgot to mention here, all these three observables, they should be extensive observables, like, meaning they should scale with the size of the system. Yeah? So again, cosmology, the volume would scale with the size of the system. The Hamiltonian integrated over all space scales with the size of the system, and so forth. Yeah? So this then suggests a coarse graining operation, as said before. Say you have a system which is given by many copies of this coherent state here with some representation labeled J, and you want to coarse grain n of those into 1, then this expectation value here suggests that you just multiply the representation by n and keep the spinor fixed. Yeah? If you do that, all the ratios of extensive observables will stay fixed, which is what should happen if you scale your system, but the intensive state the ratios stay the same, but all the extensive observables stay linear different scale. Yeah? So at this level, this is just kind of a suggestion here, because it just works for the expectation values, and you would like to ask, does it also work for everything else? Yeah, because expectation value is just one number that you get out of a wave function, and the wave function has infinitely many parameters. Okay. So this is a picture of how this coarse-graining works with those coherent states here. So here what is plotted is the absolute value squared of this coherent state for a certain magnetic quantum number. So it's probability to find kind of the state with label M in this kind of mix of states. And the blue plot points here are for j equal to 1. You could also take any other j. And then the red ones are for j equal to 4. And the only important thing here is that 4 is 4 times as much as 1. Yeah? So you need to coarse grain 4 j equal to 1s to get to j equal to 4. Yeah? So then you see here we've chosen these z's here such that this blue state is mainly peaked on the lowest possible kind of m, which is m equal to 1, and then there's a little 2, even less 3, and then they're kind of decaying very quickly. So now if you have 4 of those blue states, you can ask what are the possible kind of properties of the red state, which should be a sum of the 4 blue states. And you see, well, the blue state has a volume gap of 1, so the red state should have a volume gap of 4. Yeah, the lowest possible volume that you can get is 4. 4 times 1. And you see there is 0 here, and then the lowest possible is 1. Yeah? Now there's a funny thing that you see. You can ask, well, why does this red state not look like this blue one here? It should have a peak at 4 and then drop off. But then it's just combinatorics. Yeah? So there's just one possibility to get quantum number 4 for the red state, when all the blue ones are in quantum number 1. But to get quantum number 5 for the red state, you can have 3 ones in quantum number 1 and 1 in quantum number 2, and there are 4 possibilities to do that. Yeah? And that gives you this kind of peak here. Yeah? So this is just combinatorics that this second one is not peak at the first, but at the second. Yeah? So now this was just kind of illustrating how this works here, so let's give some further checks. So kind of thinking about the previous page, we can ask, well, do we get all the correct eigenvalues in this coarse graining? And it turns out, yes, you do by this relation here. So if you coarse grain n representations with label j, then the lowest possible thing that you can get is nj, which is also the lowest possible you can get in the representation nj. And then you can get all the higher ones, so plus adding the natural numbers. Yeah, so this works here. The first real non-trivial test is here when you ask, are also the probabilities to get those eigenvalues correct? And that turns out to be true. So for this, what you need to compute is you compute the probability to find eigenvalue m in representation nj, and that should be equal to the sum of getting eigenvalue m in the coarse system by kind of summing up all the possibilities in the fine systems to get that, and then multiplying the probabilities of each of these kind of realizations here. Yeah? So for this, you would need to take the state, take kind of many copies of it, so multiply it a lot, and then use many identities to contract these binomials and show that you get a single binomial of the coarse state. Yeah? And that turns out to be correct. Yeah? So this statement here is correct. And then you can go on and you can ask, so now it is true for the expectation value and also for the eigenvalues and for the probabilities to get the eigenvalues. Is it also true for all higher moments of the distribution? Yeah, so this is the really non-trivial test. And that also turns out to be true. So for this, it is sufficient to make the following computation. So again, here, what is written here? So you take the expectation value of any of these generators, so this alpha would run over all possible generators here, to the power n in a state, this is j here, so this is a coarse system. And here you have n systems where you have j naught, and j naught times n would be this j here. And you take the sum of those operators and you raise them to the same power here. Yeah? And this again, the computation where you need to contract many of those binomials if you get a single binomial of the coarse state. And that turns out to be true, so the kind of the computation is the one that has to be done. The first line here, the second line is just a rewriting of this first line with the multinomial formula, so we can kind of split this into a product of expectation values of generators to certain powers, and then you can also gather powers. How many powers 3 you have, for example. Yeah. So this is kind of just math that you need to follow through, but it turns out to be correct, surprisingly. Okay. So now what we have shown up to here is that this coarse graining works for a state at a certain time, but you would also like that this is dynamically stable, meaning that if you evolve the coarse state with your Hamiltonian, and you evolve the fine states with your Hamiltonian and then coarse grain, then this should give you the same answer as, so your coarse graining and time evolution should commute. And this you get for free by using the coherent states, the following property. If you have some element of SU11 of the group acting on your state, on this representation space, then you can transfer this action on the spinor. Yeah, so this is a property of this coherent state. So the spinor should be considered as the kind of the, if you want, the fundamental two-dimensional representation of SU2, which is non-unitary, but still you can act on it like this. Yeah, so this means that the dynamics, they transfer to this intensive state of the system, but not to the extensive scale. Yeah, so they don't care about this J here. Therefore, the dynamics is really J independent and therefore commutes with the coarse graining that you do. Okay. Yeah, so this means now that the coarse graining, we've seen it can be done. It is exact for all higher moments, of all moments of the wave function, and it commutes also with the dynamics. So far, what we have done is we have done this quite generally for any system that has the classical SE11 algebra, but we would like to do this more specifically now for the LQC Hilbert space in such a way that we can really see kind of a non-trivial coarse graining flow or non-trivial renormalization flow. Yeah? So again, up to now, what we did is we quantized the classical SE11 Poisson algebra. Yeah? So we would take classical cosmology, you would take certain functions in the phase space there that have an SE11 algebra and quantize them along this line. That gives you some quantum theory in terms of SE11 representation spaces, but it does not give you a quantum theory in terms of the standard LQC operators that you have. So, for example, the volume and the holonomy, the point holonomy. Yeah? And we would really like to have this in terms of the volume and the point holonomies, because that is very similar to LQG, and that kind of gives a simplified example of a renormalized LQG Hamiltonian. So therefore, what the goal of this next part of the talk is, we would like to implement this idea on n copies of the loop quantum cosmology Hilbert space. And we would like to do that in the following way. We would like to start with these n copies and the fundamental operators that you have on those n copies that are the volume and the point holonomy, which shifts the volume eigenvalue. And here is just some integers. So we take the simplest possible case, we have more computation and so forth. Just kind of integer representation labels. And this lambda here, this is kind of the fundamental scale, and you could translate that to Planck scale times the Renormalisation that we have, if you would like. But in this case, it's most easy to just work with this lambda here. Yeah. So then the task is the following. We would like to do this SU11 coarse graining. For this, it was very important to have these operators which have an SU11 algebra and are in these representations. So we would like to somehow regularize some classical operators or somehow find operators in the LQC Hilbert space so that they reproduce an SE11 algebra in representation J. Yeah? So we need a whole one-parameter family of those operators because so once you evaluate the Casimir in that representation, it should give you the correct Casimir for such a representation. Yeah? So this is a key technical task that needs to be done. Just to mention, this was also solved this year for a null representation by these people here, which is not included in these representations that we consider for a course grade. It's just some other class. Yeah? And then after you've done that, you can read off your renormalized Hamiltonian for free, because you can just consider your fundamental Hamiltonian to be the one in representation 1/2. So this acts on all the possible states in your Hilbert space. Yeah? And then you take the Lie algebra generators in representation J, and just see how they look like in terms of these functions. And this is then your renormalized Hamiltonian at level J, where kind of all the kind of high energy volume degrees of freedoms are integrated out up to the scale J. Yeah? So the scale J will be your lowest possible resolved volume. Yeah, so this can be done. This is the answer. I will not give you the details because it's so many pages of calculation. Just the ideas. So the idea is you again want the volume to be one of the operators because the volume is nice and you want it to scale with this n here. So this Jz should be proportional to the volume operator. Then, kind of owing to some classical ways in how you can do this calculation, you take the gravitational part of the Hamiltonian. This is something like sine squared times the volume. Now, we need to introduce somewhere a parameter in these operators, which will kind of later label the representation. And we saw that kind of taking a higher representation should somehow restrict the volume eigenvalues that we may have to some lower bound. So it may be a good idea to write something like square root of volume minus some lower bound, because that square root would be ill-defined if the volume goes too low. Yeah? This is just a wild guess at this point, but it turns out it's what you should do. And then you need a third operator, and this is kind of for historical reasons, this complexifier due to Thomas, which in this case is essentially just B times V in classical cosmology. Yeah, but here it turns out that you should take this combination here, it should be like a cos volume sine, and then also the other way around. Yeah, getting kind of all the ordering correct is important to get the algebra correct. Yeah, classically this computation is easy because you can shuffle all the operator or all the things around, but you need to keep track of the order in the quantum computation. So then it turns out that you can get the SU11 algebra with the following combinations. So again, this Jz is the volume, the Ky is the C here, and the Kx contains this gravitational Hamiltonian plus some square root terms that we will show on the next slide, because they're not important for this slide. And then when you have these operators, what you can do, you can just write down the Casimir operator of SU11, which is something like Jz squared minus Kx squared minus Ky squared. And you can just see what it gets, and you can match it to the possible representation that you may have. So the Casimir that you get by evaluating using these operators should be J times J minus 1, which is the possible Casimirs in these representations that you may have for SU11. And then you find that this Vm twiddle, the minimal volume, but not really the minimal volume, should be given by 2 lambda, so 2 times the scale of your quantum gravity effects times J minus 1/2. And this is just what you get out of the computation. So what you then see, kind of with no coarse graining implied, J equal to 1/2, so all possible volume values allowed, this is just 0. So this part goes away, and this just reduces to V here. Yeah, so you get your kind of more or less standard stack that you typically use in quantum cosmology. But if you do have some coarse graining, so if you coarse grain some of your systems, then this is non-zero, and you can, for example, if you want to interpret this as a certain new coupling turning on that is 0 at the fundamental scale. So then you would like to get your renormalized Hamiltonian. Remember, the action of algebra generators commutes with the coarse graining. So your task is to find the combination of algebra generators that are classically giving you a gravitational Hamiltonian, and then kind of see what they are. And this is this Kx minus Jz with this prefactor here. And then you get the following renormalized Hamiltonian. So it's renormalized at scale j, so everything below scale j is integrated out. And then you see it's again this kind of classical part here, the sine squared times the volume, with this correction here under the square root that goes away if you're considering all volumes. And then these are the square roots here that I was hiding previously. So again, see if j is 1/2, then this term goes away, this term goes away, this becomes a v plus lambda, this becomes a v minus lambda, so the sum here becomes 2v, that goes away against this 2v, so this is completely 0. However, if you're not at j equal to 1/2, where you have no corrections, then this is something non-trivial. Yeah? So what this operator encodes is it kind of encodes corrections as long as the volume eigenvalues that you have in your dynamics are somewhere close to the volume gap, which is given by this lambda here. Yeah? So this is something like a small volume correction. And it's important to see that, so you may think now I consider a very large system because cosmology happens in a very large scale. Therefore, my volume eigenvalues are very, very large. However, you should use a properly renormalized Hamiltonian, which is renormalized to that scale. And then you see also this is very large. Yeah? So kind of this Hamiltonian may act on large spins, but it kind of effectively treats them as low spins because it knows that they have been coarse-grained to some scale, which may be very, very large. It may be arbitrarily large, but it keeps track of this coarse-graining by such corrections. Yeah, needless to say, this Hamiltonian, of course, preserves the subspaces where the volume has this gap here. So the volume starts as 2j lambda and then may take any higher value. And it does that because it's a product or a sum of generators of SU11, and those have the property that they preserve the representation spaces they're acting on. So they would kind of annihilate the state if you try to go lower than the minimal one. So now the last question that you may ask is the following. What is the error that I make if I don't renormalize my system? Yeah, so, and this also connects kind of to the previous talk, because what one typically does in loop quantum cosmology is one says the universe is very large, therefore I can work with quantum states peak in very large quantum numbers, but then you use the fundamental Hamiltonian that has not been coarse-grained. Yeah, so you're acting on a very, very coarse-grained state with the UV Hamiltonian. Yeah? And the kind of question that you may ask is now, how large is the error that I make as compared to using the properly renormalized Hamiltonian that I should use at that scale? Okay? So for this, you can do a calculation here that you can also follow through analytically. So you first have to kind of specify what your kind of coarse-graining, how precisely your renormalization scale should work here. And since this is a non-graph changing formulation, so the dynamics here does not change the graph, you can say that the minimal possible volume that you have in your system is the time at the bounds. So this system is still at the bounds as usual. And you can say that at the bounds I should have the lowest possible volume. So kind of stay sharply peak at spin 1/2 close to the bounds, and then spins may become larger, and quantum effects also go down at the same time because you go to very low densities. Yeah? So all states that we use here, they're evolved with a certain renormalized Hamiltonian, and we can do this computation at any scale j, meaning for practical purposes you can say I use j1/2, I use the fundamental Hamiltonian, yeah, but I can also go to some coarse-grained scale and then say at the bounds the volume should have the minimum value in that coarse-grained scale. So that also works, but maybe simpler to just imagine that you're working with the fundamental j1/2 Hamiltonian. So then you can pick some initial values for this z's, or this sphere that was labeling a state, and then it turns out for the things that you want to compute, there's a certain combination of these z's that is important, that is given by this one here. This is captured in a real number alpha. And then it turns out that the expectation value of the Hamiltonian has this form. It scales again linearly with j, with the representation. And then the value that it actually takes is scaling with 1/alpha. And alpha is this real parameter. You can also compute the volume at the bounds time, which is just the minimal volume that you have. Again, this also scales with j, and it scales with this combinations of alphas here. And what you see is, if you want to make kind of your system very large, both extensive quantities should become very large. Here you see alpha should go to 0, then 1/0 becomes large. Here you also see if alpha goes to 0, then this is 0, and you have again 1/0. This volume also becomes very large. You can also prove this is bounded from below by 2 lambda j, which is again your volume gap at renormalization scale j. Okay. Then you just take the ratio here to define the critical density in the usual way. You get this expression here, and you see that this is bounded from above by 1/2 lambda squared, which is a standard result for the critical density if you use effective equations. Yeah, so if you use effective equations based on these operators that we had before, you get this 1/2 lambda squared, and you will of course also get the 1/2 lambda squared if you use the kind of correct quantum dynamics, but with states peak on very large quantum numbers. Yeah, so this is the kind of range of validity of these effective equations. So now we can make a plot. So what is plotted here are two things. On the x-axis there is this alpha parameter. So here for alpha equal to 1, this is kind of the regime where you want to be, where at your bounds you have mainly spin 1/2. Meaning, and then what is plotted in blue here is kind of the bounds volume normalized to the minimal volume. So this is 1 if you have kind of peak on spin 1/2, and then total volume is 2 lambda j. or the nose has a peak of the lowest positive spin. And what is plotted in red here is the density of at the bounds normalized by the critical effective density, so this 1 over 2 lambda squared that you compute with these effective equations. And what you see here is kind of consistent with what I said before. If you go to very large bounds volumes, you're in this regime where effective equations are valid, and then you get this 1 over 2 lambda squared. However, when you are in the regime where you actually have a coarse graining of many small quantum numbers, your bounds density goes down to 1 over 4 lambda squared. Yeah? So what you see from this plot here is by neglecting renormalization and just keeping track of this one observable in the bounds density, you are you're overestimating the critical density by a factor of 2. Okay. So let me briefly conclude. So what has been done is an analytic coarse graining for homogeneous and isotropic spacetimes. By doing that, we have obtained a renormalized Hamiltonian, which kind of acts on large spins, but it holds the dynamics of many small spins. And we have seen an error estimate for a self-observable, which is the critical density at the bounds. Yeah? So there are some takeaway lessons that I want to emphasize here. So the first one is the result is not surprising. Yeah? I mean, couplings turn on if you renormalize. This is very well known. What is somewhat surprising is the possibility of an analytic treatment. And if you kind of try to compute the dynamics for quantum gravity, you should be aware that the physics of many low spins, which we expect to be the physical regime, may be different from that of few large spins if you don't renormalize, and therefore also from the effective equations. Outlook is obviously generalized. This was done for the simplest possible model. It was good to see that it works there. Of course, you would like to see if it works in some other cases. Does this do these SU11 techniques I discussed work for general groups? That would be question number 1. And then, given many more interesting physical systems, black holes and so forth, what are the algebras of observables that I can produce there? And that may map to some group algebras, so I can apply that if it works for general groups. So, thank you for your attention, and I guess this is my present to Jurek. This is your Renormalised Hamiltonian.
Thank you. Let us start the discussion.
So, I have a question regarding your renormalization step. And if I understand correctly, then your step keeps the volume fixed, right?
Well, kind of the volume operator is always the volume operator. That's, you could say it like that.
Yeah, so my understanding of renormalization is that you input some things that you're sure of, and so in order to get results in the renormalized theory that you didn't know before. So if you keep the volume fixed, then you're quite confident that the volume operator already gives you the correct volume in the first place because it is fixed in the final renormalized theory. So I'm asking where this confidence comes from, because the way I see it, one should rather keep some relations fixed that one expects to hold axiomatically in the renormalized theory in order to obtain results, for example, like the volume, because one doesn't yet trust that the observables one has started with are the correct ones that one would expect to hold.
Okay. So maybe I say in some other words what is done here, and then you can say if you agree or disagree. So what is done here is you say, given some Hamiltonian that may be, the Warsaw Hamiltonian for the scalar field, or the Tiemann Hamiltonian, or the AQG Hamiltonian, assume that this Hamiltonian is correct, and assume that it acts on a state that is peaked on many small spins. The question that is answered here is, what is the effective, or can the dynamics be effectively captured by a few large spins? And if yes, what is the Hamiltonian that generates the same dynamics as the Hamiltonian that you previously defined and kind of declared to be true for the small spins? So this is a question answered here. So this does not take into account that maybe your operators may completely change in the RG step or so. So it assumes that the fundamental system that you have is the correct one, and it just answers how that would look in a coarse scale.
Yes, that's what I understood from your talk. But the question is, so what do you want to do with it? Because so one approach to renormalization would be to use it to obtain some kind of continuum theory or some kind of so one would expect the renormalized theory to have some well, to be more fundamental in some sense than the theory one started with. So if you start with a theory in which you have a volume operator and you trust it completely, then this volume operator will already give you the volume in the final theory which you want to compute in the final theory. So, so the question maybe asked differently is what is your renormalized theory supposed to give you? So do you think of it as a kind of better theory than the initial one? Or
no, here I just think of it as an effective theory that captures the dynamics of certain coarse observables with a new Hamiltonian. It's like a block spin transformation. You take an Ising model, you declare the Ising model to be correct, and you ask if I integrate or decimate some of the spins, what is the effective Hamiltonian that acts on pure spins.
So you don't think of it as some kind of continuum limit?
No, because I'm not really sure whether that's appropriate and whether that's... It's certainly not the case here, and I really don't know whether that's the appropriate notion that you should think about.
Okay, thank you.
Okay, there are no more questions and comments. Let us thank